Science Olympiad Class 9. Is matter around us pure?
Introduction. As we look around, we can see that most of the matter around us exists as mixture of two or more pure components. For example, seawater, minerals, soil, etc. are all mixtures. Mixtures are constituted by more than one kind of pure form of matter, known as substance.
What is a mixture? A pure substance contains only one kind of particle. An impure substance contains particles of more than one kind and is called a mixture. A mixture is made up of two or more substances mixed in a random way without forming any new substances.
Solution. A solution is a homogeneous mixture of two or more substances. We come across various types of solutions in our daily life. Lemonade, soda water, etc. are all examples of solutions. We think of a solution as a liquid or a gas dissolved in it. But we can also have solid solution, say alloys, and gaseous solution, say air. A solution has a solvent and a solute as its components. The component of the solution that dissolves the other component in it is called the solvent. The component of the solution that is dissolved in the solvent is called the solute. Colloidal solution. Stir a small quantity of blue ink with a large quantity of water. The solution turns blue. Leave it aside without disturbing it. After some time, there is a deposit with a clear solution on top. Try filtering the solution. There is no residue left. Send a beam of light from a torchlight through the solution. The path of the beam is seen in the solution. Ink is an example of a colloidal solution. The size of the solute particles is bigger than that in the true solution, and hence it settles after some time. The solute, however, cannot be filtered by ordinary filter paper. The colloidal solution shows a property called Tyndall effect. The Tyndall effect is the scattering of light by colloidal particles. This accounts for the beam of light being visible in the ink solution. Types of colloids are shown in the table.
Solutions can be classified based on amount of solute as follows. Dilute solution is a solution in which the solute quantity is small in a given mass of solvent. Example, a dilute sugar solution has very little sugar dissolved in large quantity of water. Concentrated solution is a solution in which the solute quantity is large in a given mass of solvent. For example, a concentrated solution of sulfuric acid has very little water. The quantity of sulfuric acid is large. Saturated solution is a solution that cannot dissolve any more solute without changing the temperature. Example, a saturated salt solution at a given temperature cannot dissolve any more salt. Unsaturated solution is a solution that can dissolve more solute at a given temperature. Example, an unsaturated salt solution at a given temperature can dissolve more salt. Supersaturated solution is a solution that has more solute than a saturated solution at a given temperature. Expressing concentration and numerical on concentrations of solutions. Weight fraction is a ratio of the weight of solute to the weight of the solution. Weight fraction of solute equals the ratio of weight of solute to a weight of solution equals weight of solute by weight of solution. Weight fraction of solvent. The ratio weight of solute to weight of solution equals weight of solvent by weight of solution. Weight percentage is the ratio of the weight of solute to the weight of the solution expressed as a percentage. weight percentage of solution equals the ratio of weight of solute to weight of solution expressed as a percentage equals weight of solute by weight of solution into 100. Weight percentage of solvent equals the ratio of weight of solvent to weight of solution expressed as a percentage equals weight of solvent by weight of solution into 100. Volume fraction is a ratio of the volume of solute to the volume of solution. Volume fraction of solute equals the ratio of volume of solute to volume of solution equals volume of solvent by volume of solution. Volume fraction of solvent, the ratio of volume of solvent to volume of solution. Volume percentage is the ratio of the volume of solute to the volume of the solution expressed as a percentage. Volume percentage of solute equals the ratio of volume of solute to volume of solution expressed as a percentage equals volume of solute by volume of solution into 100. Volume percentage of solvent equals the ratio of volume of solvent to volume of solution expressed as a percentage equals volume of solvent by volume of solution into 100. What is a suspension? Solution can be classified based on the solute particle size into true solutions, colloids, and suspensions. Colloids and suspension. Colloids. In colloids, the solute particle size is between 10 to 1000 angstrom units. Suspensions. In suspensions, the solute particle size is greater than 1000 angstrom units. Properties of suspensions. A suspension has the following properties. A suspension is a heterogeneous mixture. The particles of a suspension are not dissolved in the solvent but suspended. The particles of solute can be seen with the naked eye, as the size is above 1000 angstrom. A beam of light focused on a suspension scatters on entering the solution. Over time, if a suspension is not disturbed by shaking, the solute particles settle at the bottom of the container and can be separated by filtration. Example of suspension. Rainwater collected in a glass tumbler looks muddy as it contains suspended particles that settle over time at the bottom.
Properties of colloids. A colloid is a heterogeneous mixture. The size of particles of a colloid is too small to be individually seen by naked eyes. Colloids are big enough to scatter a beam of light passing through it and make its path visible. They do not settle down when left undisturbed. That is, a colloid is quite stable. Take some full cream milk in a vessel. Centrifuge it by using a centrifuging machine for 2 minutes. What do you observe on churning the milk? Explain how the separation of cream from milk takes place. The principle is that the denser particles are forced to the bottom and the lighter particles stay at the top when spun rapidly.
Concept of dispersion systems. Dispersion system. Any mixture made up of a substance distributed as minute particles of solid, droplets of liquid, or very tiny particles of gas bubbles through another substance is called dispersion system. The substance dispersed is called dispersed phase, and the continuous medium around it is called dispersed medium. Both the dispersed phase and dispersed medium can be in any physical state solid, liquid, or gaseous. In true solutions, both dispersed phase and dispersed medium are indistinguishable and appear as one. The particle size is 1 to 10 angstrom. In colloids dispersed phase, solute size is 10 to 1000 angstrom. Two phases exist, dispersed phase and dispersed medium. Solute particle size is greater than solvent particle size. In suspensions, dispersed phase size is greater than 1000 angstrom. The solute particles precipitate after some time. Example of dispersion systems are given below. Separating the components of a mixture. A mixture has two or more substances mixed in a random way. The component of a mixture can be separated by using physical methods like filtration, boiling, fractional distillation, fractional crystallization, etc. The exact method that is used to separate the mixture depends on the physical properties of the components.
Fractional distillation. To separate a mixture of two or more miscible liquids for which the difference in boiling points is less than 25 K, fractional distillation process is used. For example, for the separation of different gases from air, different fraction for petroleum products, etc. The apparatus is similar to that for simple distillation, except that a fractionating column is fitted in between the distillation flask and the condenser. A simple fractionating column is a tube packed with glass beads. The beads provide surface for the vapors to cool and condense repeatedly as shown in figure.
Separation of mixtures. Magnetic separation. Using magnetic separation can separate a mixture that contains iron with other non-magnetic substances. Sedimentation. Standing the mixture and pouring out the upper layer of liquid after the fine particles settle down at the bottom can separate a mixture containing very small particles as a suspension. Filtration. Passing the mixture through a filter paper can separate a mixture that contains a solid as an insoluble component in a liquid. The insoluble solid will remain on the paper and the liquid passes through the filter paper. Evaporation. Heating the mixture over a flame when the liquid evaporates, leaving the solid behind, can separate a solid with high melting point dissolved in a liquid with low boiling point. Boiling. Boiling the mixture when the gas boils off from the liquid and is connected separately can separate a gas dissolved in a liquid. Liquefaction. Lowering the temperature or increasing the pressure on both can separate a mixture of a gas in gas. The gas that is easily liquefied separates as a liquid and is removed. Diffusion. Using the difference in their rates of diffusion can also separate a gas-gas mixture. The heavier gas moves slowly. The gases are passed through a series of porous membranes, when the lighter gas passes through the membranes faster and can be collected separately. Some examples are given below. Chromatography. Taking advantage of the difference in rate at which the different components in the mixture move, the components are separated. A heavier component or stationary phase component will move less when compared to a lighter component or mobile phase component of the mixture. Type of chromatography: paper chromatography, thin layer chromatography, column chromatography. Paper chromatography takes advantage of the difference in adsorption of components of a mixture and the different solubility of the components of the mixture. The mixture is placed on a special filter paper. The paper is placed in a special chosen solvent. The component that is strongly adsorbed or that which is not soluble in the solvent will move along the paper slower. Conversely, the component that is not adsorbed well or that which is more soluble in the solvent will move along the paper faster.
Immiscible liquid separation. Let us try to separate kerosene oil from water using a separating funnel. Pour the mixture of kerosene oil and water in a separating funnel. Let it stand undisturbed for some time so that separate layers of oil and water are formed. Open the stopcock of the separating funnel and pour out the lower layer of water carefully. Close the stopcock of the separating funnel as the oil reaches the stopcock. The principle is that immiscible liquids separate out in layers depending on their densities. Different gases from air. Air is a homogeneous mixture and can be separated into its components by fractional distillation. The flow diagram shows the steps of the process. If we want oxygen gas from air, we have to separate out all the other gases present in the air. The air is compressed by increasing the pressure and is then cooled by decreasing the temperature to get liquid air. The liquid air is allowed to warm up slowly in a fractional distillation column where gases get separated at different heights depending upon their boiling points.
Air is liquefied by the following steps. First step. Dust particles in air are removed by passing air through filters in water. Second step. The air is passed through dilute caustic soda when gases like carbon dioxide and sulfur dioxide are removed. Third step. The air is now cooled when moisture present in it solidifies to ice, making air dry. Fourth step. The pure air is compressed to a pressure of 200 atmosphere, due to which its temperature increases. The hot compressed air is passed into a cooling tank. Fifth step. Next, the cooled air is repeatedly compressed and expanded into an evacuated chamber through a fine nozzle. Due to Joule-Thomson effect, every cycle of compression and expansion results in a drop in the temperature of the air. As the compressed air comes out of the nozzle, its pressure suddenly decreases and the temperature falls. The cooled air is then compressed again and sent through the nozzle into an evacuated chamber. Repeated compression and expansion of the air leads to a fall in temperatures for every cycle till it liquefies. Sixth step. The liquid air is at a temperature of minus 200 degrees Celsius. The liquid air consists of nitrogen at minus 195.8 degrees Celsius, while that of liquid oxygen is minus 183 degrees Celsius. The difference in boiling points is used to separate the two liquids by fractional distillation. The liquid air is very slowly warmed to minus 195 degrees Celsius when nitrogen starts boiling off. Nitrogen is collected by compressing into steel cylinders. On further warming, oxygen boils off at minus 183 degrees Celsius. Oxygen gas is collected after compression in separate steel cylinders. Rate of dissolving of a solute in a solvent depends on size of particles. Smaller the particle size, more the rate of dissolution. Agitation. Agitation increases the rate of dissolution as it helps in dispersing the saturated regions to make way for unsaturated regions. And temperature. Temperature in general increases rate of dissolution as kinetic energy of the particles increases. The fractional crystallization makes use of the fact that different salts have different solubilities at a given temperature. This difference in physical property, differing solubility, is used to separate a salt from a mixture with other salts. Water is heated to a temperature of say 80 degrees Celsius and the mixture is added. The mixture is continuously added while stirring. Still, no more mixture can dissolve. Now the solution is cooled to room temperature when the substance that dissolves to a smaller extent has lower solubility will be precipitated out as crystals. Copper sulfate can be separated from a mixture of the impure salt by fractional crystallization.
Element. Elements can be normally divided into metals, nonmetals, and metalloids. Metals usually show some or all of the following properties. They have a luster, shine. They have silvery gray or golden yellow color. They conduct heat and electricity. They are ductile, that is, can be drawn into wires. They are malleable, that is, can be hammered into thin sheets. They are sonors, make a ringing sound when hit. Examples of metals are gold, silver, copper, iron, sodium, potassium, etc. Mercury is the only metal that is liquid at room temperature. Non-metals usually show some or all of the following properties. They display a variety of colors. They are poor conductors of heat and electricity. They are lustrous, sonorous, or malleable. Examples of non-metals are hydrogen, oxygen, iodine, carbon, coal coke, bromine, chlorine, etc.
Characteristic properties of inert gas elements. All inert gas elements are gases. Inert gas elements do not react with other elements. There are 6 inert gases known to occur naturally: helium, neon, argon, krypton, xenon, and radon. Characteristic properties of metalloids. Metalloids show the properties of both metals and nonmetals. The first 20 elements with their atomic numbers and mass numbers are given below.
Compounds. A compound is a substance composed of 2 or more elements chemically combined with one another in a fixed proportion. Difference between mixtures and compounds. Mixtures. Elements or compounds just mix together to form a mixture and no new compound is formed. Compounds. Elements react to form new compounds. A mixture has a variable composition. The composition of each new substance is always fixed. A mixture shows the properties of the constituent substance. The new substance has totally different properties. The constituents can be separated fairly easily by physical methods. The constituents can be separated only by chemical or electrochemical reaction.